Summer Undergraduate Research at Florida 2023. Hello, my name is Melany Perez Matias, hailing from the beautiful island of Puerto Rico, as evident from the insignia at the bottom left. While I currently reside in the quaint town of Aguada, my academic pursuits have led me to the University of Puerto Rico and Maya West. Here, I am diligently pursuing a bachelor's degree in mechanical engineering with my anticipated graduation date set for May 2024. During this summer, I had the opportunity to embark on an exciting journey, flying all the way from San Juan, Puerto Rico to Gainesville, Florida. The purpose of my voyage was to actively participate in a research project. Within this endeavor, I have been an integral part of the STEAM Herbert Wertheim College of Engineering, specifically associated with the Nuclear Engineering Science Department. I am an integral member of the Florida Advanced Multiphysics Modeling and Simulation Group, which operates under guidance of Dr. Justin Watson. Within this group, our primary focus lies in conducting cutting-edge research to create advanced analysis tools dedicated to nuclear reactor safety analysis. Our research encompasses a wide array of areas within reactor analysis, spanning from fuel management and core design to comprehensive thermal-hydraulic analysis of nuclear reactors. During my journey, I have had the privilege of working closely with Joel Latimer, who served as my PhD mentor. Throughout this enriching experience, I have proudly contributed to the Herbert Wertheim College of Engineering as a dedicated participant in the Nuclear Engineering Sciences Department, where the pursuit of innovative solutions and the advancement of nuclear engineering remain at the heart of our endeavors. The title of my research is Pressurized Water Reactors Pin Power Reconstruction Using Machine Learning Models. Literature review. Pressurized water reactors belong to the broader category of light water reactors and were among the earliest commercial power reactor types developed in the United States. A typical cross-sectional view of a pressurized water reactor reveals that water enters the pressure vessel through the inlet nozzle, surrounds the core acting as a reflector, passes through the core to be heated, and then exits the vessel via the outlet nozzle. The water in a pressurized water reactor remains at high pressure to prevent boiling. In a sense, water is pumped under high pressure into the reactor core, where it gets heated by the energy produced through atomic fission. In the context of predicting parameters for fuel assemblies in light water reactors, a specific neural network architecture called LatticeNet is employed. LatticeNet combines densely connected and convolutional elements to effectively make these predictions. Convolutional neural networks operate by sliding a kernel, or filter, across a two-dimensional image, performing a multiplication of the kernel's value with the corresponding image pixels. This process allows CNN to efficiently learn and recognize patterns in images or other two-dimensional data. Pin power reconstruction within a nuclear reactor fuel assemblies contain multiple fuel pins. Pin power refers to the power distribution within these individual pins. Accurate pin power reconstruction is essential for safe and efficient reactor operation. Machine learning models involve developing algorithms that allow computers to learn patterns from data without being explicitly programmed. In this context, machine learning models are likely being used to predict or estimate the pin power distribution based on various input data. To summarize, pressurized water reactors are a type of light water reactor designed to generate power. LatticeNet is a neural network architecture used to predict parameters for fuel assemblies in light water reactors And CNNs are neural networks particularly well suited for processing two-dimensional data such as images. Objectives: develop machine learning surrogate models to supplement expensive, high-fidelity core simulators. Our objective is to create a versatile solution applicable to both high-fidelity and low-fidelity simulations. This includes developing a surrogate model capable of accelerating high-fidelity solutions, performing pin power reconstruction for low-fidelity simulations, and accommodating scenarios with evolving geometries, such as field performance modeling. In these applications, the physical dimensions of the field change both radially and axially, leading to variations in the Coolant gap. Produce model with accuracy of lattice code and runtime of nodal code. Our aim is to design a model that achieves the accuracy of a lattice code while maintaining the fast execution time characteristic of a nodal code. Produce approximate models rapidly without spending human effort fine-tuning. Efficiency in model development is crucial, and we seek to rapidly produce accurate models without extensive manual fine-tuning. To achieve this, we are exploring efficient methods for automating hyperparameter optimization. Produce models that are robust against out-of-bounds data. Additionally, our focus is on creating models that demonstrate robustness against out-of-bounds data. We aspire to develop models that can yield reasonable results even for data distributions that the model has not encountered during training. Overview: develop a methodology for the application of deep learning to light water reactor modeling and simulation. Develop a general architecture for predicting high-fidelity parameter distributions in both single and multi-assembly regions based on computer vision methods. Generate a database of high-fidelity inputs and outputs. Develop a method to determine if a target model will fail to give a physically realistic answer, even for regimens with no training data. Explore methodology generally to novel distributions separate from the training distribution. Our main focus was on devising a deep learning methodology tailored for the application in light water reactors. However, it is essential to note that the methodology's principles are not limited to light water reactors exclusively. We opted to use light water reactors for practical reasons since we had access to relevant software and data. The methodology we developed possesses the potential to be adapted to various reactor systems, including Gen 4 designs, as long as the inputs and outputs can be visualized and formulated in a similar manner. Consequently, we established a versatile framework named LatticeNet, which represents a general architecture. The figure on the right provides an example of the LatticeNet's overall structure. Methods: convolutional neural networks. The initial proposal was to use convolutional neural networks for digit recognition. CNNs are a well-known approach, particularly effective in the image processing and computer vision tasks. However, they impose a constraint that data must be in a two-dimensional input format. In CNNs, a kernel is applied across every spatial portion of the input image to capture different features. Multiple N plus N filters are used in a single layer of the CNN, and successive convolutional layers are combined to form convolutional stacks. These convolutional stacks are instrumental in learning database priors, eliminating the need for manual feature engineering. The process involves scanning the input image with filters, and the results are multiplied with the input and stored in the convolutional layers. Once all images are processed through the CNN, the convolutional stacks can be flattened and fed to a multi-layer perceptron network for further processing and classification. The multi-layer perceptron network is used to make the final predictions based on the features extracted by the CNN. This combination of convolutional and fully connected layers enables CNNs to effectively recognize and classify complex patterns and features in images. LaticeNet pinwise error. The average percent error per pin reveals that in comparison to other burnable poison groups, no poison, Pyrex, and the average percent error per pin for each burnable poison in the test set is relatively small, all being less than 0.2%. Among them, no poison, Perez, and Weber exhibit the smallest average errors, while IFBA and gadolinium have the largest. Despite this observation, the reason behind iodine-containing burnable absorber group having a larger error compared to other burnable poisons remains unclear. Further investigation is necessary to understand the underlying factors contributing to this higher error for the IFBA group. Data generality nodal powers. The initial result showed good improvements in predicting pin power distribution for problems larger than one assembly. My part on this project was to develop the full core model. Future plans include coupling my 3x3 mini-core and my full core to the single assembly using LaticeNet machine learning to predict normalized powers at the pin levels to produce accurate pin level results. That sums up my summer research experience. Future plans. My future aspirations involve applying for fall 2024 admission to the PhD program in nuclear engineering science at the University of Florida, Worthing College of Engineering. Additionally, I am also looking forward to pursuing a master's degree in interior design at the NYC Interior Design School. Here are some snapshots showcasing my summer experience, a part of my research journey. I would like to extend my gratitude to the individuals and institutions who have played a significant role in making my research journey a success. First, I would like to express my deepest appreciation to Mike Nazareth, the Director of Undergraduate Research, and also Ashley Wilson, the Coordinator of Undergraduate Research at the University of Florida. I am also grateful to the University of Florida for generously providing funding and housing. A special thank you goes to Dr. Justin Watson, my mentor, whose expertise, encouragement, and mentorship have been invaluable in shaping my research path. Their insightful guidance has not only deepened my knowledge, but has also inspired me to strive for excellence in my work. I am equally thankful to Joelle Latimer, my PhD mentor, for the invaluable insights and support during my research journey. Last but not least, I extend my gratitude to all the wonderful individuals I have had the pleasure of meeting through this program. Thank you all for being an integral part of my research endeavors and for making this journey an unforgettable and rewarding one.